Hello, welcome to lecture 6. In this lecture, we're going to pick up with doing some examples of standing waves in tubes. We'll pick up this time talking about standing waves in tubes. We said last time that we can get standing waves in columns of air in a tube when we meet certain conditions. So the boundary conditions for a standing wave in a column of air is that, first of all, if we're at a closed end, that means that there's a displacement node. It means the air molecules can't move. There's no motion. But there's a pressure antinode because there's a big variation in pressure when the air molecules get squished or spread out a bit. So that's our boundary condition at a closed end. At an open end, we have a displacement antinode because the air molecules are free to move in and out of the tube. At the open end, we have a pressure node because the air molecules at the open end are in equilibrium with the outside air. So those are our boundary conditions. Our conditions for frequency, if we have a tube that's open at both ends, and this also turns out to be true for a tube closed at both ends, we'll get standing waves when the frequency of sound is equal to some integer times the speed of sound in the medium in the tube, and that's generally 344 meters per second for air, divided by 2 times the length of the tube. If our tube is closed at one end and open at the other, sometimes that's called a stopped tube or a stopped pipe, you get frequencies generating standing waves equal to n times v over 4L. The 4 comes from the different boundary conditions. Here what's important is that n is only equal to the odd numbers. So a tube closed at one end only has the odd harmonics, whereas a tube open at both ends has the full set of harmonics. In this example, we have an organ tube playing music, and we know that there are standing waves at 786 Hertz and 1310 Hertz. There are probably standing waves for frequencies under 786 and frequencies over 1310, but there are no standing waves for frequencies between 786 and 1310. That's what it means by successive harmonic frequencies. We'd like to find the fundamental frequency, we'd like to find the nature of the organ tube, what's the harmonic number, and what's the length of the pipe. Seems like we're trying to find a lot with only a little bit of information, but this is something we can definitely do. Let's tackle part A first, finding the fundamental frequency. So there are multiple ways to go at this. I'm going to show you the way I like the best. I know that one frequency is 1310 Hertz. I know that the next lower frequency is 786 Hertz. And I know that standing wave frequencies are always evenly spaced. So I'm going to find delta F. What's the difference between successive frequencies? So that's 1310 Hertz, subtract 786 Hertz. So the difference between any two successive frequencies is 524 Hertz. Okay, so now what I'm going to do is I'm going to find the lower frequency under 786. What's the next lower frequency that produces a standing wave? Well, that's going to be 786 Hertz, subtract 524 Hertz to get 262 Hertz. Now, if I tried to go to a next lower frequency, I would subtract 524 again. That would give me a negative number. That can't be right. So that means that 262 Hertz must be the fundamental. So this is F1 because it's the lowest frequency. All right, there's part A. I found the fundamental frequency. So all I do is I subtract delta F from each successive value until I get the lowest value. The lowest value is the fundamental. All right, part B. This kind of rolls right from our part A. We know tubes that are open at both ends, or open-open, they have delta F equal to the fundamental. For tubes that are open at one end and closed at the other, they have delta F equal to 2 times F1. So in our problem, we have that delta F is 524, F1, the fundamental, is 262, So in our problem, delta F is equal to twice F1. Therefore, our organ pipe is open-closed. Some people will argue that an organ pipe has to be open at both ends, and that's not actually true. Organs can be either way, it depends on the manufacturer. I may or may not have taken a frequency analyzer into my church and used it during Mass to figure out for the organ pipes in my own church. They were actually open-closed. All right, part C. What harmonic number corresponds to the frequency of 786? Well, what we know here is that for the fundamental 262 hertz, that's the fundamental, that's n equals 1. Then we know if a tube is open at one end and closed at the other, we only have the odd harmonic numbers. So the next higher frequency, 786, has to be n equals 3, and then the next higher would be 1310 hertz, that would be n equals 5. So it asks what harmonic number corresponds to the frequency 786, that would be n equals 3. All right, part D now. Find the length of the organ pipe. What we know for tubes that are closed at both ends, Fn equals n times V over 4L. Got to make sure you get the right equation here. If it was open at both ends, you'd be using NV over 2L. That means L is equal to n times V over 4 times F. Now you can use any pair you wish here. You can use n equals 1 and frequency 262. You can use n equals 3 and frequency 786, or you can use n equals 5 and frequency equals 1310. They'll all give you the same answer. I'm going to use the n equals 1 value. It doesn't say anything about the speed of sound in air, so let's assume that the speed of sound in air is 344 meters per second. So that gives us 1 times 344 meters per second divided by 4 times our frequency F1, 262 hertz. And that gives us the length of our organ pipe. Hang on, I'm just going to grab my calculator and double check my answer. 344 divided by 4 divided by 262, 0.328 meters. So 32.8 centimeters for the length of our organ pipe. Now here's an interesting application of tubes that are closed at one end and open at the other. That would be your ear canal. So in your ear canal, the outer part of your ear is open to the atmosphere, but the inner part where you have an eardrum is closed because you have the membrane between the two surfaces. So we could figure out what harmonics or what standing waves or what normal modes happen inside the human ear. To do that, we'll write down our equation for frequency for the standing waves. Fn is equal to n times V over 4L, where n is the odd harmonics, 1, 3, 5, 7, 9, so on. What do we need to know here? V is the speed of sound in the air inside your air canal. Now that speed of sound is not 344 because the air inside your air canal is probably not 20 degrees. It's probably 37 degrees body temperature. So we'll use our equation to find V, 331 meters per second times the square root of 37, average body temperature, plus 273 divided by 273 to give us a speed of about 353 meters per second. So that's the speed of sound in air in your ear canal. The length of an ear canal varies among humans, but for most people it's about 2.5 centimeters. So there's probably some variation where it's a little smaller and some where it's a little bigger, but it's always in the ballpark of 2.5 centimeters. Okay, let's see the frequencies of the standing waves we can get. Our first standing wave would be the fundamental, would look something like this. F1 is 1 times V over 4L. Put that through the calculator and we should get 3,530 hertz. Our next standing wave we could get in our eardrum. Let's try and draw it. So Go node to antinode. The next standing wave looks kind of like this. So F3 is 3 times V over 4L, or 3 times F1. That would give you the same answer. That's 10,600 hertz. And our last one, we squeeze in more of a wave. So that standing wave looks something like this. And then that's F5 equals 5 times V over 4L, or 5 times F1, to get 17,700 hertz. Now, hearing is pretty cool. What it means that we get these resonant modes at these frequencies is that human beings tend to be very sensitive to these particular frequencies. When we do a hearing test, when a person hears these approximate frequencies, people say that these are much louder than other frequencies. So I'm going to give it a try. I'm going to play this online tone generator. I put the web address there if you want to fool around with this by yourself at home. Heads up, this might be a little bit loud, so if you have earbuds in, you might want to turn the volume down before you turn it back up so it doesn't hurt. So keep an eye on the frequencies and see, do you notice it gets very loud for around any of these frequencies? Now, being the experimentalist I am, I would probably try and use this tone generator to see if I could figure out the length of my eardrum. Last thing we might point out, the reason I didn't calculate F7 or F9 is because frequencies with those values of N, those standing waves, they're higher than audible frequencies. They get bigger than 20,000, so an average human wouldn't be able to hear those. For our last example now, we have a tube that's 50 centimeters long. We'll write the length in meters. It's capped at both ends, so that means our tube is closed, which means that the frequencies of the harmonics or the normal modes is n times v over 2l, where n is an integer. Standing waves are excited by tapping one end. We know the speed of sound in air is 344 meters per second. We're given that the speed of sound in helium is 999 meters per second. Part A, find the frequencies of the first 3 harmonics in the tube in air. That's not written there, but it is implied. So for our harmonics, F1 is 1 times V over 2L, 1 times 344 meters per second, divided by 2 times 50 centimeters, or 0.5 meters, gives us a fundamental frequency of 344 hertz. The next frequency, F2, we can find by doing 2V over 2L, or we can do 2 times F1. That will give us 688 hertz. And then our third frequency, F3, we can do 3V over 2L, or we can do 3 times F1, and we should get 1032 hertz. Okay, so for part B, if the tube is then filled with helium, how would those frequencies change? Before you do the calculation, you might decide for yourself, do you think it's going to get bigger or smaller? Okay, let's go ahead and do the calculation. F1 is going to be 1 times V over 2L. This time V is the speed of sound in helium, 999 meters per second. We're dividing that by twice the length of the tube. And we get for our fundamental frequency 999 hertz. Our second frequency, F2, is twice our fundamental, equals 1998 hertz. And our third standing wave will have a frequency of 3 times our fundamental, which is 2997 hertz. Okay, part C I'm going to leave for a homework problem for you. Find the wavelengths associated with each of those frequencies and draw the standing waves in the tube. I won't do this as a video, but I will write up the solution and post it with the notes. Okay, let's take what we've learned about standing waves on strings and standing waves in columns of air and apply it to music. We get music when we make waves on strings, so we pluck a string and it vibrates, we get certain standing waves. Or if we make standing waves in columns of air by blowing across the top of the column of air. Waves on strings would apply to things like a guitar or a banjo, and waves in columns of air apply to woodwinds like clarinets or flutes. So the instruments make sound, or we use the instruments to make sound that we hear and listen to. Now, if strings work one way and woodwinds also work a certain way, why is a banjo different from a violin? And why is a recorder different from a cello? Those things sound very different. Okay, I'm going to do a demo that hopefully will explain it. What I've got here, this is an app on my cell phone. It's called a spectrum analyzer. There are loads of these for free in the Google Play Store and in the App Store. What it does is it tells you the frequency of sounds that are present. While I'm talking, you see little spikes coming up. That's telling you the frequencies of the sound of my voice. I'm going to make two sounds. Neither of them are going to be particularly musical, but hopefully one is a little better than the other. Okay, first I'm going to whistle. You look at the frequency. Okay, there's my whistle. Not super. I know some people are great. I'm not one of them. Hopefully what you noticed was there was only one frequency present in my whistle. Okay, next I'm going to make another sound, also not very musical, but hopefully a little nicer. I'm going to sing a little tiny la note. La 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 la. Okay, hopefully my little la sounded better. And hopefully you noticed that there were lots of frequencies present. Let's just do that again. La 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 la. Okay, the whistle had one, but the singing had a bunch. That's the reason why some instruments sound nicer than others. Some instruments can support many resonant frequencies, and some only support a few. The more resonant frequencies you can have, the nicer your music will sound. This is actually a reason, and I think some people are going to know where I'm coming from here. This is the reason why it sounds so nice when you sing in the shower or if you sing in a small corridor. When you sing in those small spaces, you actually set up resonances in the standing waves in the air columns, and it gives you just a fuller tone of your singing. So I guess I would invite you next time you're in the shower, please belt out a song. You'll probably enjoy the way that it sounds.